So actually, I mean, I'm going to finish my lecture yesterday first, and then we'll start talking about von Kampen diagrams. So first of all, the correction to this example. So it should be A here. This is an example of a Stallings graph for the subgroup H of a free group given by two generators, A and B. So H is a subgroup given by these three generators. And okay, so what we see here, we have A, B, A square, right? And then A inverse B square, and then A, B, A inverse, no, wait a minute. A, B, A inverse, B. So that's a, and what you can see that we can read every word in the group H. So we can think about this Stallings graph as a finite automaton, right? Because what is a finite automaton? It's a graph, finite graph, with directed labeled edges. And we should have initial and terminal vertices are the same here in this example, right? So basically, every word, like when we're going along the graph, we read with labels of edges, and every word which we can read as a loop beginning at H is an element of H, right? Because every loop is a composition of three simple loops corresponding to generators, right? And and actually all what we can read here, it must be a composition of these three simple loops. And therefore everything we can read here is an element of H. So the language accepted by this automaton is exactly a set of elements of H. Now, what is the algorithm like if you asked, because we are going to prove like more properties of a free group using this automaton. So how to construct it algorithmically? So suppose you have, okay, let me, first of all, I mean, we can notice that this automaton has one-way reading property. This means that no two edges outgoing from the same vertex are labeled by the same letter, right? Because this is a property of a Schreier graph. We want a part of a Schreier graph. So there is only one edge labeled by a given letter. And then, okay, so this is like just from graph theory. So a path is a sequence of edges with exponents plus or minus 1. And we say that a path is reduced if it contains no subpath of this. Right? So in this graph, actually reduced paths are labeled by reduced words. Okay, so every element of H is a loop in this Stallings graph. So this gives an easy procedure to solve a membership problem. Given an element, to decide if the element belongs to a subgroup. So we just have to see whether it is accepted by this automaton, whether we can read it as a word, as a label of a path beginning at H, label of a loop beginning at H. So how do we construct Stallings graph? So let me just explain by hand wavings. So suppose we have this group, this subgroup, three generators, right? So first, we just take a vertex V0 which is going to correspond to H, and draw loops corresponding to these generators, right? So we draw these loops, okay. So now we would like to fold some edges, to identify some edges. Actually, what we would like to do, we would like to identify the edges like outgoing from the same vertex and labeled by the same letter. So we have to identify edges and the terminal vertices of these edges, right? Because so we need to have this one-way reading property. Okay, let's see. What we have here. So this is A and this is A. So 3 yellow vertices, and this is also it. 3 yellow vertices are going to be identified, and 2 orange vertices are going to be identified, right? So on the next step, and we got this. Now, let's look at this graph. Still, there are vertices such that there are 2 edges labeled by the same letter and outgoing from this vertex. So we have to identify these 2 yellow, and this is also B in this direction. So we identify these 3 yellow vertices and corresponding edges. Got this. Now, okay, what else? For this vertex, there are 2 edges labeled by B. Again, these yellow vertices. So we have to identify them. And there are more. So, like, if you look at this vertex, there are 2 edges labeled by B from this vertex. So we have to identify these edges. And now we can check all the vertices, so everything has a one-way reading property. Now, okay, so basically, I mean, you can do it as an exercise to show that this automaton, or like this graph, accepts the same language as the initial one, right? Because it requires some, whatever, to say something. It requires some proof, but it's basically a few sentences. Like that, this automaton accepts exactly the same language, the same reduced words as the initial automaton. And the initial automaton accepted exactly like elements of H. And the thing is that when we did these foldings, we actually did not change the language which is accepted. So, but it like one has to look at it more carefully. Of the word problem, about like how geometrically to see which words represent identity in a group given by a presentation. So what is Van Kampen diagram? Also the other name is Dehn diagram or disk diagram, so it's all synonyms. So suppose we have a finitely presented group. Also suppose that relations are cyclically reduced, and RC, let it be the cyclic closure of R. So we add to relations all cyclic shifts of relations. I mean, these elements are also equal to identity in the group, right? So we can add them all. So they're all there. Now, consider finite, connected, oriented, based, labeled planar graph, where each edge, each oriented edge is labeled by a generator. Okay. Now, the base point should be in the boundary of this unbounded region of R2 minus delta. So let's just, we have something like this. So we have, or maybe like this, right? Directed. And labeled. So we have to label it by elements of S. So suppose it's, but, okay, before I label it. So what is on the labels? Like for each bounded region, the boundary is labeled by a word in this cyclic closure of relators. So basically the boundary, also we need a base point somewhere. Let's take it here. So the boundary of a region, of a bounded region, must be labeled by relators. So for example, if my relators, let's say, suppose S is like, S is A and B, so suppose I have relations. R1 is, okay, B inverse, say A. So this face, I labeled one face by this relation, And then, oh, we need to do something here. But whatever, each phase is, I'll show you examples later. Each phase is labeled by a relation. Also, usually we label phases like clockwise by relations. And then, okay, so the boundary word on the diagram is the word which we read on the boundary of the unbounded region. So this is like unbounded region. So we read it, usually we read it like counterclockwise. Okay, so, and in this case we say that delta is a Van Kampen diagram for this word W. So W is, we read W here, over the presentation. Okay, now what is, why do we need the diagram? Because the following lemma, one can prove the following lemma, and actually it's sort of, one can see from the picture what's going on. So the following, suppose we have a finite presentation and the word W. Then the following are equivalent. First of all, the word is equal to 1 in this. Okay, the group is now gamma. I mean, this is a picture I borrowed from Tim Riley lectures on filling functions. So you can find Google lectures on filling functions. He has such a beautiful drawing that, you know, you cannot stand just to steal them. So, okay, the word is equal to 1. And, okay, what does this mean? This means that the word is a product of conjugates of relations or the inverses, right? So the word is a product of conjugates of relations is the inverses. And so this is, both of this is equivalent to the fact that this word admits a Van Kampen diagram. That one can draw a Van Kampen diagram so that on the boundary of this diagram we can read our word W. Okay, and like bounded region of the diagram have relations written on the boundary. Now, how to see this? This is like one can see this. So suppose our word is product of conjugates of relators. Let's just draw this. So this is our base vertex. So it's U1, R1. R1 labels the disk. U1 inverse times U2, R2, U2 inverse. Okay, so so on the boundary of this, so this is a diagram, right? On the boundary of this diagram, we can read our word W. But now again, we can do foldings. Actually, we can fold the edges labeled by the same letters, right? And then we can transform like this diagram into this diagram and sometimes into this diagram. But it's not necessarily, it doesn't necessarily can have like just, you know, vertices which are not on the boundary of any region, actually, like here it may have this form. Okay, so now we define the area of the word. So now again, like we put geometry to the word problem. So the word is W is equal to 1 in this group. Conjugates like of relations to the inverses, which need to like to show that this word belongs to a normal subgroup generated by relations. So the word lives in W lives actually in the free group, but it belongs to a normal subgroup generated by relations, right? So it can be represented like this, and the area of the word is a minimal number n. Or we can say that it is a minimal number of like of these bounded regions in a diagram corresponding to this word. So it is actually, in some sense, it is an area. So we can also view this diagram as a two complex. So like we can attach two cells to each bounded region, right? Two cells with a boundary corresponding to the relation. So, okay, now, so this is an example. So this is a diagram for Z3. So it's a free abelian group. So abelian group with three generators, and we have three relations like this. So the presentation is A commutes with B, B commutes with C, and A commutes with C. So we have like what? A, okay, no, B, A. B, A inverse, B inverse, AB is equal to 1. And so all three commutators are equal to 1. So, I mean, this is a diagram, so we can draw it on the plane. And let's read. So this is the base vertex. So we can read this word, B, A inverse, C, A inverse, and so on. So we can read this word on the.
Is this equivalent to like tori being glued together?
You can think about this that way, yes. But I mean, in principle, it is just whatever, planar picture, it's a planar graph, or planar, so it's finite planar to complex. Like if we glue faces here, so we can think about planar to complex, and again, like edges are labeled and directed. So you can think about a diagram as about a graph, or you can think about a diagram as about a two complex, like if you put faces. So again, like if it is a two complex, so then edges labeled by generators, and we have two cells corresponding to each relation, and around the boundary we read the word which is equal to 1. So, okay, different words have different diagrams, right? And the same word may have different diagrams too, depending on how we represent it as a. Yeah, I mean, okay, this is actually a picture in the Kelly complex. Let me, I'll better talk about this here. So let's talk about the presentation complex. So to each finitely presented group, we can assign a two complex, which has this group as a fundamental group. So what do? So first, we take a rows. Take a graph which is a rows labeled by the generators. Then we take like two cells with relations labeling the boundary, and then attach these two cells so that the boundary of the cell is attached to the path in this graph labeled by the same word. Okay, so. And then we get a two complex. Now, the fundamental group of this complex is G, because, okay, so it's generated by these loops, and as soon as we attach two cells, it becomes equal to 1. So that's exactly, the fundamental group is exactly our group G. So to each group G, we can assign this two complex. Now, the universal cover, K tilde, of this is the Kelly two complex. Like we can take universal cover of this complex, and we're going to get a Kelly two complex. Now the one skeleton of this Kelly two complex is a Kelly graph, actually. So one can get Kelly graph. Like again, think about this as about exercise, but okay, the universal cover is a complex, right? And then like what are the vertices? What is the zero skeleton of the universal cover? It's a set of vertices corresponding to group elements, right? So this one vertex covered by like all the group. So edges correspond to vertices which have distance 1 between them. So if you take a universal cover of this two complex, so we have Kelly two complex, and the one skeleton is a Kelly graph. And actually, we can think about the diagram also as about like a mapping into a Kelly complex, right? Because if there is a diagram like this, then there exists a closed path in the Kelly complex, which is like the same as this diagram. Okay, so that's a presentation complex. Now let me show you a couple of examples. So let's begin. So yeah, if we return to this picture, so this is how we see the diagram in the presentation complex. So it's a filling of the closed path corresponding to the boundary of the diagram. Okay, now 2 examples. So Z2. So what is a like presentation complex for Z2? So we write this commutator on the boundary of the square and glue the square like to this like wedge of circles, and we get a torus actually if we do this, right? Because we have to glue A's and B's, so we get a torus. And right, Z2 is a fundamental group of a torus. Now this is a Kelly complex, this is a universal cover of it, and one skeleton is a Kelly graph. Now this is what you're going to do like as an exercise to work with it today. So we have a basically group with this relation, and if we take this 8 gon and glue it to the wedge of circles, you'll get an orientable surface of genus 2. So basically this is a fundamental group of the orientable surface of genus 2. It's a product of 2 commutators, A and B and C and D. And okay, and this is a universal cover. So this is how it looks like. And as an exercise, what you're going to do, you're going to see what kind of words you can get, which words are equal to 1 in the in this group. So you have to try to somehow glue together to construct different diagrams, right? And maybe convince yourself that every word which is equal to 1 actually contains half of the relation as a subword. This is what Gulnara defined yesterday. This is a small cancellation group. Right? This is a small cancellation group, and what is lambda 1,8, right? So this is a small cancellation group. 1,7. It should be less. Yes, it should be less than 1 over lambda. The pieces of this word. Like we take all secret permutations of this word, right? And then the pieces, like common beginnings of relators. Okay, so this is just 1 letter. 1 letter has length 1, and it's shorter than 1/7 of both relations. Less or equal than 1/7 of both relations. Okay, so 2 examples. Another example. This is a like famous Baumslag solitaire group. Like this group is a whatever. It's a good counterexample to many like properties. So this is BS like 1, 2. Right? So if we conjugate, the relation says that if we conjugate A by B, we get A square, right? And okay, so again, this is how to build the presentation complex, and this is a part of the Kelly complex, like part of the universal closure. But you see, like what is going on here. I mean, the areas of these diagrams become very, very large because you know, A, every time A becomes A square. So here in this Kelly complex, so this corresponds to B. So these edges, vertical edges, correspond to B, and edges going like horizontally correspond to A. Right? So we have 1 cell, but then we have to glue 2 cells to it, and then we have to glue 4. Like to each of 2 cells, we have to glue 4. And but actually, I mean, I'll return to this. But then we can shift like 1A, and then on the other side we glue like the same picture, but we glue. So you can think about this also as about the diagram, but like the contour of this diagram is hidden there. But we will come to this when we start counting the areas of the words. Like, we just notice that actually areas are very large in this group. Okay, so now what is a Dehn function? Again, one of the characterizations of the word problem in a group is a Dehn function. So take H loop in the Kelly-2 complex of finite presentation P. Okay, so area of this H loop is the minimum area, like of one Kampen diagrams, which span this this loop. So area of a loop or area of a word, as we defined it already, it is a minimal area of the minimal one Kampen diagram corresponding to this word, right? And then, okay. So the Dehn function is the maximum of areas of H loops in the Kelly complex such that the length of H loop is less or equal than n. Let's look at this. So basically, we go over all words equal to 1 that have length n, compute areas of these words, so basically areas of minimal one Kampen diagrams corresponding to these words, and take the maximum of this, right? So it's a maximal area for all words of length n, length less or equal than n. Okay, so actually, I mean, this indeed has a geometric meaning. Like, so this area function is, so if we have a finite presentation of the fundamental group of a closed Riemannian manifold, then this area function is equivalent to the area in the universal cover. Now, what means equivalent here? Equivalent means, like we say, that two functions, okay, f is asymptotically less than g if, okay, there exists c greater than 0, that for any n, like f of n is less or equal than, okay, c g of cn plus c plus, I think, cn plus c. Okay, so this is f asymptotically less or equal than g, and then f and g is asymptotically equivalent if and only if, okay, f is less or equal than g and g is less or equal than f. So we have to talk like up to asymptotic equivalence because I mean, as soon as we change system of generators of the group, or everything changes. But the class of asymptotically equivalent functions is actually a quasi-isometric invariant. So if two groups are quasi-isometric, then like their Dehn functions are asymptotically equivalent. Mm-hmm.
Here, the area of the universal cover of the manifold, is that a function of n or y?
No, we have loops there, right?
Okay.
So we have loops, and we can talk. Okay, right. It's not a function of n, but if we take loops of integer length, then I mean, then we're going to have like this equivalence. Like, but also we can, you know, that in the Kelly complex, in a sense, we can extend the metric to R. But just let's think about like this. So if we have a loop in the universal cover of integer length, then it has the same like equivalent. Because I define this function for n, and I don't want to go into like details. Okay, so basically, I mean, it is real area. It is, I mean, it has real geometric meaning, this area function, this Dehn function. Okay, now let's see what, again, let's look at the examples. So, again, suppose we have an abelian group given by two generators. So the area is asymptotically equivalent to n square. Right? It's like in the Euclidean space. So we know that the area in the Euclidean space is a square of the perimeter. So this is what we can expect. And in any abelian group, so the area is equivalent to n square. Now, this is our fundamental group of orientable surface of genus 2. And the area is a linear function. Actually, one can prove, and I don't know, maybe I'll do it in the fourth lecture. Maybe let's discuss this. So every hyperbolic group, so this group has small cancellation, right? And therefore it is hyperbolic. Like every hyperbolic group, so hyperbolic groups are characterized that the area function is linear in hyperbolic group. So if a group has a linear area function, it is hyperbolic. And hyperbolic group has linear area function. Now, it's to show this. And again, we know that like if we have a hyperbolic metric space, then the area is a linear function of the perimeter. Okay, how to? Maybe we have to define, like to explain this for hyperbolic groups, we have to define what is Dehn presentation for a hyperbolic group. So Dehn presentation. So if G is a hyperbolic group, delta hyperbolic group. So if G is a delta hyperbolic group, then the presentation, okay, the asymmetric presentation of G is called the Dehn presentation. Symmetric presentation of G, let's S A R. So symmetric means that this set is symmetrized. We have all cyclic shifts. It's called Dehn presentation if like for any W, which is equal to, for any reduced word W that is equal to 1 in G, W contains more than a half of some of the defining relators as a subword. So W contains more than 1/2 of a relator in R as a subword. I mean, we have a finite number of relators, symmetrized relators. So hyperbolic group, every hyperbolic group has such a presentation, can be given by Dehn presentation. So it's such a presentation that every word which is equal to 1 in the group contains more than a half of one of the defining relators as a subword. We're talking about reduced word. Our defining relators are reduced words. So, like for example here, every word which is equal to 1 will contain more than a half of this, of a cyclic shift of this relation. Now this requires a proof which is like a bit longer than I have time to do, but if we know this, then it is easy to show that the area function is a linear function, right? Because let's suppose we have a diagram. So this is our word W. Okay, so this word W contains more than a half of some defining relation, right? Suppose it's here. So this is more than half of the defining relation, let's say R1. Okay, then, I mean, it's not good drawing because it's like this. So this is R1, cyclic shift of R1. Now what we got now on the boundary, also W, the length of W, because it's N. Right? Now we have a new diagram with a boundary having length at most n minus 1, right? Because this path is shorter than this path. This was more than half of the defining relation. Okay, and then we can keep doing this by induction. So we know that suppose the area of the diagram of each diagram of words less than n is a linear function with some parameters. Then, like by induction, we show that the area of a diagram for a word of length n is also a linear function with these parameters. We remove one like cell and we decrease the length by 1. So it is a linear function for any hyperbolic group. Also, like you can read, for example, the proof that every hyperbolic group has Dehn presentation. For example, in Breisenhefliger book, there is a section there. Mm-hmm.
When you say you remove a cell, are you identifying?
No, what I mean, I don't really to remove it. I mean, but okay. So if W is equal to 1, now the contour of this new diagram is also equal to 1, right? But it is a word which is shorter than W, right? And so for this word, we know that actually, if we have a Dehn presentation, then the area is going to be exactly n, right? Because but is going to be exactly n. But if you have some other presentation, so I mean, the Cayley complexes are going to be quasi-isometric, but the function is going to be asymptotically equivalent to n, but not necessarily n, like the area function. So it is just a linear function. I mean, I got a linear function for a particular presentation, for a Dehn presentation. So this means that for every other presentation, it's going to be like in the same equivalence class, so linear function. Okay, now bounds-like solitaire group, this example. Okay, so this is what we do. Like, let me see. Let's compute the area of this diagram. Like, so how many B? 1, 2, 3, 4, 5, 6, and then 1A. So what we did, like, this is a sort of a strip of cells having A to the n on the boundary, right? And then we shifted it 1A to the left and glue it like this. So the boundary of the diagram is, if we read it like this, it is A, then B, 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 then A inverse, no, A again, and then again B 6 times, then A inverse, then B 6 times, A inverse, B 6 times. So I can write what we got. I mean, do you follow me with this diagram? I mean, run who doesn't follow. Okay, so W is, if I read it beginning here. If I read it beginning here, so what I read? I read A, B to the 6, A, B to the 6, A inverse, B to the minus 6, A inverse, right? B to the minus 6. So this word is equal to 1. But how many, what is the area of this diagram? Like here we have what? 2 to the power 6 cells, right? So the area is, area of W is like greater or equal than whatever, 2 to the 6 for this diagram. Okay, now if instead of 6 you take n, right? So you're going to have that the Dehn function is exponential and it is asymptotically equivalent to 2 to the n. Okay. Now, examples of Dehn function. So for finite groups, whatever the function less or equal than linear, right? Because exercise. Now for free groups. So what do we have for free groups? Actually, I mean, there are no one Kampen diagrams, like non-empty one Kampen diagrams, because there are no relations. So, so the Dehn function, I mean, we just, whatever we say, it's linear or it is 0. Or now, for hyperbolic groups, we know, so it's linear function. Now, for finitely generated abelian groups, it's a quadratic function. Now, for three-dimensional integral Heisenberg group, so this is a group of matrices. I think it was initially it was a question solved by Steve Gersten, like to show that Heisenberg group has non-quadratic Dehn function, right? So the group is a group of all matrices with identities, group of 3 by 3 matrices with identities here. So A, B, and C are integers. Okay, now it has a presentation, can say it's generated by A, B. Actually, it is generated by A and B, but I write C. So C is a commutator of A and B. And then C commutes with A. And C commutes with B. So it is a 3-step nilpotent group. 2-step nilpotent groups, 3 by 3 matrices, 2-step nilpotent groups. Now, if you have class C free nilpotent group on 2 letters, then the Dehn function is equivalent to n to the power C plus 1. I mean, this is hard as an exercise. So again, like there are papers. Again, there is Gersten's paper, the first, then the proof was simplified, but like it is not an exercise. For Heisenberg group, it can be done as an exercise today, actually. But in general, for like, I mean, do you know an easy proof for C free nilpotent group? Do you know an easy proof of like of this? No? For Heisenberg group, yes. Let's do it as an exercise today, and you're responsible.
It's like trying to do it now, but no.
It's not an exercise for the Heisenberg group, I think. But again, like I mean, I know what I mean. Have not been thinking about Dehn's functions like for the last few years, right? So I know Gersten's paper which proves this. It is like it is whatever, like 10 pages paper, right? But he proves other things. But since then people were working, so maybe there is a simple proof. I don't know. Like maybe we can try to do it today. I mean, it's in principle one has to get another presentation and. One has to, so basically to prove that it is not quadratic, you construct a particular diagram, right? So with a counter like length linear in n and the area which is not quadratic. And this, I mean, this can be done not very difficult way. Now, how to prove that it is exactly n cube? So let's think of the exercise. What I know are papers. Okay, now in a sense, Dehn function it may be considered as a complexity of the word problem, but there are flaws. So what is like what we can say? So for a finitely presented group, the following are equivalent. So the word problem is solvable. The Dehn function is recursive. And the Dehn function is bounded above by a recursive function. I mean, okay, so if the word problem is solvable, you can you can construct a recursive function, right? So you can construct a function which gives a maximum area for words equal to 1, words of length n equal to 1. So then the Dehn function is recursive, and okay, then it is bounded by a recursive function. If it is bounded by a recursive function, okay, take number n. You know, like the function is recursive. You know f of n. You know that you for a given word of length n is equal to 1. If and only if you can construct a diagram with the area less or equal than this f of n, right? So you can try all of them and decide whether this word is equal to 1 or not. So the word problem is decidable. But when I'm saying you can try all of them, so the time complexity, I mean, there are, so, right, so groups with undecidable word problem, the Dehn function is not bounded by anything. So this is like some hydras and very complicated, because, I mean, you don't know. Like if you could bound the Dehn function, you could solve the word problem. There is no, like the function is not bounded by any recursive function, so it can be very large. But like groups with large Dehn function, so this is, the thing is like, it's sort of, it is a complexity of the word problem, but it's sort of geometric complexity, not necessarily a time complexity. I mean, you can have groups with very, very large Dehn function and with word problem which can be solved very fast. It's because you don't really, to solve the word problem, you not necessarily have to construct this diagram, right? So it's a different question. For example, have some time. Let me show you an example of like of a group which okay, for example, this the same bounds like solitaire group 1, 2. It is a subgroup of GL2Q, and A goes to this matrix, B goes to this matrix. Okay, and we know that it has exponential Dehn function, right? But to solve the word problem, okay, so we have a word in A and B, we just multiply the matrices and see whether they represent the identity matrix. So it's fast, like for 2 by 2 matrices. And again, like when you multiply the matrices, you don't really construct one Kampen diagram for a word, you just multiply matrices. So like it is polynomial solution of the word problem and exponential Dehn function. And there are other examples. Okay, I think I'll stop for today. Yeah, and next time we're going to go back to free groups and like to prove some property separability property for subgroups of free group, residual finiteness and such things. Okay, thank you.